Okay, last lecture we have just solved one problem on Bernoulli's type of differential equation. Let us practice by solving couple of more problems on that. Problem number 2. Y dash is equal to x cube y cube minus xy. Get me the solution in the form 1 upon y square is equal to. Okay, it seems this is the same problem which was solved earlier. So answer is x square plus 1 plus c raised to x square. Question number 3. 3 divided by dx plus 2 upon x plus 1 y is equal to x cube upon y square. Express your answer. Okay, show me your answer, whatever it is. Okay, the answer for this is y cube into x plus 1 bracket square is equal to x raised to 6 upon 6 plus 2x raised to 5 upon 5 plus x raised to 4 upon 4 plus c. Now it's problem number 4. X divided by dx plus is equal to y square log x. Get me answer in the form is equal to 1. You cross check your version of algebra of answer with my y inside bracket log ex plus cx bracket complete is equal to 1. Or
सर तुम्ही हे सोडून दाखवू शकाल का?
हो दाखवतो. Just a moment. 1 upon y is equal to log x plus 1 plus cx. This is one step before that. This also should be correct. Okay, let me quickly write down the solution. This is given to us, which is equal to 1 upon y square divided by dx plus 1 upon xy is equal to 1 upon x log x. Put 1 upon y is equal to v implies minus 1 upon y square dy by dx is equal to dv by dx. Substituting that, we get dv by dx minus 1 upon xv is equal to minus 1 upon x log x. Integrating factor e raised to integral minus 1 upon x dx, which is equal to e raised to minus ln x, which is equal to 1 upon x. Integrating factor is 1 upon x. Therefore, solution is v into integrating factor v into 1 upon x is equal to integral of 1 upon x integrating factor into q of x minus 1 upon x log x dx, which is equal to minus integral log on x square log x upon x square dx, which is equal to log x upon x minus integral 1 upon x 1 upon x dx, integration by parts, is equal to log x upon x plus 1 upon x plus c. In fact, plus c should have been written earlier only. Okay. This is v into v is equal to log x plus 1 plus cx implies y inside bracket log ex plus cx is equal to 1. Hope I am writing it correctly, and you can cross check, find out any error and let me know. Let me give you the last of Bernoulli's form. 5. Ink change 5. dy by dx plus x inside bracket x plus y is equal to x cube inside bracket x plus y raised to 3 minus 1. This is a little tricky. Maybe report whatever way you want. I will write down the solution eventually. Okay, if we rearrange this little bit, dy by dx plus 1, this minus 1 comes to the other side. This is first term plus x into x plus y is equal to x cube into x plus y bracket cube. Okay. This is, if you look at this, this is d of x plus y upon dx. If you could visualize this, if we differentiate x plus y with respect to x, we will get 1 plus dy by dx. So instead of writing this term, what we can write is, why I have written it equal to this. I think this term should be replaced by this. Then you have equation in x plus y. There are 3 people which are x plus y. You can replace them by z and solve it. So eventually that what you get is x plus y raised to minus 3 dx plus y dx plus x into x plus y raised to minus 2 is equal to x cube. So this is differential equation in x plus y with respect. So let x plus y raised to minus 2 is equal to z. You get minus 2 x plus y raised to minus 3 dx plus y upon dx is equal to dz upon dx, and therefore minus half dz by dx plus xz is equal to x cube. This is your standard FOLD. So answer is z e raised to minus x square. Integrating factor is e raised to minus x square is equal to integral minus 2x raised to 3 e raised to minus x square dx plus c, which is 1 upon x plus y bracket square equal to c e raised to x square plus 1. That is what is your answer. Okay, so this is Bernoulli's. Now let us move. And so first order linear differential equation. First order, first degree. Linear means degree 1. That is what we have studied. Now method for solving differential equations. Of first order and of higher degree. Then first. Okay, degree of differential equation is not equal to 1 but little higher than 1. So the differential equation f x comma y comma p. P is the differential coefficient of first order and its powers are going to be higher degree. So it is represented like p raised to n nth plus p1. आता p1 कशासाठी are the functions of x comma y. So maybe I will take some other q1 p raised to n minus 1 plus q2 p raised to n minus 2 plus dot 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 plus qn minus 1 p plus qn is equal to 0. It can be arranged like the polynomial we arrange in descending orders of x or descending powers of x. You can consider the given differential equation as a polynomial. And then what are these q1, q2s? q1, q2, qn are functions of x comma y, x and y. This, I mean, can be any, but without differential coefficient. Differential coefficient is p. P is dy by dx. Okay. So broadly, the methods to solve this, there are 3 ways to solve this. I mean, it is trial and error. So whichever is better, convenient, you should solve using that. And maybe sometimes you can say we cannot solve it. I mean, that is how it is. One, solvable for P. Second, solvable for Y. And third, solvable for X. So these are the 3 people sitting here in the differential equation. You check what is convenient to you to solve and deal with it. We will see all the 3 ways of doing it. 56%. Okay. So first, solvable for P. Let us consider solvable for P. Now let us learn by how is this going to look like. F x comma, let me reduce the thickness, this is too bad. F of x comma y comma p, if it is solvable for p, it is going to look like factors. So it is going to be p minus f1 of x comma y into maybe I will make this normal brackets only. The solution, the given differential equation, if it is a polynomial in P, it can be factorized like this: P minus f2 of x comma y dot 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 p minus x comma 1. So if you have factorization of the given differential equation like this, then this is going to be equal to 0. That is what we are solving. So it is good to solve each and every bracket, and that will give you solution of the given differential equation. The given differential equation will, I mean, the so one of the, suppose there are n solutions and they will satisfy the original given differential equation. Okay, that is a simple way of looking at this differential equation. Just like polynomial in P and factorize, if you are lucky, you will get good factors and you will solve it. Let us learn by taking example. Go to page number 7. Page number 7, problem number 1. Okay, question 1. xy p square plus 3x square minus 2y square times p minus 6xy is equal to 0. I mean, initially I have to give you simple. What is p? P is dy by dx, and therefore it is a differential equation. Easy? Do it. Solvable for y. Solvable for p, sorry. Yes. Px minus 2y into py minus 3x plus 3x is equal to 0. So you have dy by dx into x is equal to 2y, or dy by dx into y plus 3x is equal to 0. These are supposed to be your two differential equations which you are supposed to solve and get the answer. It is, I think, variable separable, therefore the answer is y is equal to cx square, or second answer comes out to be 3x square plus y square minus c is equal to 0. Okay. So now they are not looking alike, they are totally different functions. They will have totally different graphs, but any one of them will satisfy the given differential equation. That is the fun part of it. I mean, domain, the function itself are totally different, but they satisfy the original differential equation, and there is no, I mean, y is equal to c parabola, and this is not parabola. This may be something else, or a hyperbola or an ellipse. It is a plus sign in between, so hopefully it is ellipse. This is ellipse. This is parabola. They don't have anything in common. So these are the solutions. Now I expect a question from you at this stage. If you are not asking, I have to ask you. But I give you some time to ask me question on this. Okay, the question at this stage is, we have solved two differential equations as a solution for the given differential equation. So I have right now written c and c both the places as an integration constant. Is it the same c which is here as well as here, or you mean c1 here and c2 here? What is the correct periodical justification? What is the correct answer and what is the justification? Okay, so as to answer this question, let us learn how do we get differential. Suppose simple problem, let me give you y is equal to mx plus 10. What is this? These are the straight lines of slope m. What is the integral curve of corresponding to this? I mean, I am calling it integral curve because I am interested in eventual differential equation. Y-axis intercept is always 10, and it is all the lines passing through this point with different slopes. So m is my unknown. M is my arbitrary constant. So if I want to create a differential equation out of this with respect to x, I do it like this, 0. And hence, if m is equal to dy by dx, my differential equation, suppose this is your normal equation with one constant, but corresponding differential equation of which this is going to be the solution is y is equal to dy by dx times x plus 10. This is your differential equation, whose solution is going to be this. So you are just replacing the arbitrary constants by differential coefficients. Let me take another example where we want to get rid of arbitrary constants. Say for example, we have algebraically little bit complicated, but let me have it. X minus h bracket square plus y minus k bracket square is equal to 10. Let me have this numerical constant. Now, how many arbitrary constants are there in this equation? Of course, this is circle. Okay, this is circle. We center at h comma k and radius 10. So all congruent circles lying in xy plane everywhere, you select x comma h comma k and you get a circle. This is what it is. This is what this is. Yes or no? It's a family of congruent circles. H comma k will determine which circle you are. Now, if we really want to convert this this equation into a differential equation, whose solution is this? Let us try to do it. You help me because it is bad algebra. With respect to x, I am differentiating. I will get 2 into x minus h. Derivative of this is 1. So 1 plus 2y minus k into derivative of y dy by dx is equal to 0. Is that correct? That gives me value of y minus k is equal to I will not jump. I am old. I should perform couple of steps. So maybe this is 0 now. Yes. So x minus y is equal x minus h is equal to y minus k minus of y minus k divided by dx. And therefore, why not I should keep it like this? X minus k h is equal to this. Therefore, if I substitute this back over here, I am getting rid of one constant, which is, so 2 is gone, so minus 9. Okay. Now, wait a moment. Now, this is our first time we have differentiated. Now, suppose we differentiate it one more time. What we get is 1, that is LHS differential. Why should I do it here? I should do it upstairs only. Okay, this is first derivative that you are using. And because I know I am supposed to differentiate one more time, 1 is 2 is gone, 1 minus h is gone, plus I am supposed to differentiate 1, so y minus k into d2y by dx square plus dy by dx into dy by dx square is equal to 0. This is second. Is that right? And therefore, from second I get y minus k is equal to minus dy by dx bracket square minus 1 upon d2y by dx square. Okay, so I have got y minus k with me in terms of differential coefficient, and then if I substitute this y minus k back into the equation 1, what I will get is x minus h is equal to x minus h is equal to y minus k times dy by dx. So minus dy by dx bracket square minus 1 upon d2y by dx square. This is the minus of this. So let me make it positive. So that is taken care into dy by dx. Okay. So now I am aware that y minus k looks like this, x minus h looks like this. Therefore, using these two values of y minus k and x minus h, I write my differential equation. Bracket square plus this bracket square is equal to 10. This is your differential equation. This fellow will get into this bracket, this fellow will get into this bracket is equal to 10. And then if you observe this differential equation, it is independent of the arbitrary constant. It is independent of arbitrary constant, but it has got differential coefficient. So in real life, in real physics, you don't get arbitrary constants, you get differential. You get differential coefficients. And that is why we suddenly get a differential equation from the nature. And we are supposed to go back and what is the solution of that differential equation. I mean, whatever algebra that we have studied so far, we did not have these differential coefficients with us, and therefore at that point we used to stop and we did not solve the problems beyond that. But in physics or in maths, you will now have the equations which will involve differential coefficients as a model that you make. If you, if you get the differential equation directly from the nature, you need to have some method to retrieve what the integral curve it is talking about. And therefore with these two examples, what I'm trying to explain it to you is, if differential coefficient is of order 1, then arbitrary constant is 1, because in this case there was only one constant m, and we could get rid of that constant by differentiating only once. However, in second curve that we have said, there were two arbitrary constants h and k, and therefore to get rid of h and k simultaneously, we had to differentiate it two times. So number of arbitrary constants are going to be equal to the order of differential equation. Samajhte ka? That is what is the, theory, not really the theory, but I am trying to give you the insight of how these arbitrary constants are produced. It is because the differential coefficients take their place. And if there are two constants, we will not be able to get rid of both the constants unless and until we differentiate it twice. If there are three arbitrary constants, we will not be able to get rid of all the three unless we differentiate three times. That is what needs to be understood, and therefore coming back to our original equation, the degree of this differential equation is 2, but order of this differential equation which is given to you is 1. It is p, it is dy by dx, and therefore if it is dy by dx, then arbitrary constant here and here same. It is going to be same. Otherwise it is going to be chaos. Now, as far as integral curves are concerned, we said if c is equal to 1, we end up getting parabola, standard parabola for this equation. And if c is equal to 1, we end up getting standard ellipse. I'm not sure whether it is this way or that way, but it is ellipse. So these are the two curves. The moment you specify c is equal to 1, all other integral curves will disappear from that xy plane, and only these two will survive. This is the diagram of the solution of your differential equation if c is equal to 1. That is how it is. And therefore, for every value of c, you will have one curve from this family, another curve from that family, and that is all about it. That is what it is, and therefore, no matter, you have to keep watching what is the order of differential equation, and it is yet another cross check also. If your order of differential equation is 3 and you ended up getting only two constants, then it is completely wrong. You must end up getting three distinct constants when you solve order 3 differential equation, and so on. That is what is the explanation that I would like to give as far as that constant is concerned, and it is extremely important. Questions? Quick, easy. Question, I think 2. 56%. P square minus py minus x into x plus y is equal to 0. Answer. P square minus py minus x into x plus y is equal to 0. So dy by dx minus y is equal to, or dy by dx is equal to minus x. Correct. Therefore, first solution is x plus y plus 1 minus c raised to x multiplied by x square plus 2y minus c is equal to 0. This is the solution of the multiplication form मध्ये. Okay, so if either this bracket is 0, you are satisfied. I mean, you are satisfying the equation, or this bracket is 0, you are satisfying the equation. Okay. Good. Question 3. The fourth minus x plus 2y plus 1 p cube plus x plus 2y plus 2xy p square minus 2xy times p is equal to 0. Fourth degree, first order differential equation. Answer: y minus c, y minus x minus c, 2y minus x square minus c, y minus c raised to 2x is equal to 0. This is the solution of the given differential equation. I have two more problems on this. Solve them. Fourth, xy p square plus x square, sorry, xy p square minus x square plus y square times p plus xy is equal to 0. Answer for this is x square minus y square minus c into x minus cy is equal to 0. Last one of this type. Fifth, x square p cube plus y times 1 plus x square y p square plus y cube p is equal to 0. These are solvable for p's. Okay, answer for this y minus c, first bracket, y minus c raised to 1 upon x, second bracket, and xy minus cy minus 1 is equal to 0. This is the solution. Chala, okay. Now the next. Solvable for x. Now, typically if this is a differential equation, you should be able to write it in the form x is equal to function of y comma p. So you should be able to explicitly say that x is equal to something, and in RHS you don't have x. If this is the situation, if this is the case of given differential equation, if given differential equation can be represented like this, x is equal to some function of y, then the approach is going to be as follows. Now, if we differentiate this equation with, this is the trick and technique to solve differential equation, huh? But logical and legal steps, no shortcut or no not something which is not legal, we are not going to do. So what we do is differentiate with respect to y, both sides. Then what will happen? Dx by dy will be there here, so we can write this as 1 upon p, because our p is dy by dx, and this is our differential coefficient of the given differential equation. So we are supposed to solve this and get a constant, but now we are stuck, we cannot deal with it, but we can write x as function of y and p, and therefore we have decided to differentiate it with respect to y, and also RHS you differentiate with respect to y, and whatever expression that you will get, you deal with it, solve it, and then eventually you should not forget that your p is the differential coefficient, and by solving, after differentiating with respect to y, you will solve it and you will get a relationship of p, x and y, p, x and y, and if you could separate that relationship, p is equal to something of x and y, you can directly put that value of p in the given differential equation, and that is what is going to be your solution. Okay, little confusing if I am talking general like this. Let me give you one problem. You try your level best to solve it, otherwise we will solve it together afterwards. But I give you sufficient time to solve. Question 1, solvable for x. Question 1, 6y square dy by dx bracket square plus 3x dy by dx minus y is equal to 0. Now you will see that this is degree 2, first order degree 2 differential equation, because dy by dx has power 2. We have y square, we have y, and only x. That is why it becomes solvable for x. Try to do it. After some time I will solve it on board. Correction in the last answer. It seems there should be plus in between, xy plus cy minus 1. Okay, first thing that we should do is we should separate and put x on one side. If we do that, We can always call this p, so that first of all it will look like 6y square p square plus 3x p minus y is equal to 0. Okay. Now I should put it in such a way that it is x is equal to, I have already written with me, so you cross check whether it is correct. 1 upon 3y by p minus 2y square p. Correct? Is this okay? I think it is correct. So now we have decided to differentiate with respect to y. So dx by dy, which is equal to 1 upon p, which is equal to 1/3 into p into derivative of y with respect to y is 1 minus y into dp by dy upon p square. This is the derivative of first term minus 2 y square dp by dy minus 2 y minus 2yp. Is that correct? Minus 2yp. 2y and 2y. So minus 4yp. Okay, cross check whether this is correct. Now what we are supposed to do is just simplify it. Further, suppose we multiply by p everywhere, then I have 1 in LHS and 3p square in RHS. Can you simplify this and check whether you get this? Say for example, 3p is equal to p minus y dp by dy minus 6p square y square dp by dy minus 12p cube y. I mean, I will wait till the point you get simplify everything and get to this particular equation. This is 2p plus y dp by dy plus 12p cube y plus 6p square y square dp by dy is equal to 0. Okay. This gets factorized into two factors, 1 plus 6p square y into 2p plus y dp by dy is equal to 0. Okay. Now, we are going to ignore this because here it is p square is equal to minus 1 upon 6y. And of course, depending upon the parity of y, it is going to give us some results, but we will leave it aside and concentrate on this. And therefore, we get 2p plus 2y dp by dy is equal to 0, which is 2 dy by dx, 2 dy by y plus dp by p is equal to 0. It seems it is variable separable type, and hence you can solve it and get final equation as y square p is equal to constant. Okay, so up to this point it is fairly simple. Therefore, this implies p is equal to c upon y square. Okay, now in our mind we have p as dy by dx, so we are supposed to solve the given differential equation. Means what we are supposed to do is that this differential equation which is given to us, in which we have this P here, this is P and this is P. Now, if we could replace this P by relationship with, if I can replace P as function of x comma y comma constant, then that is what it is. That is what it is. That is what we want. And therefore, the relationship is now being substituted by this quantity wherever P is, and that is what is the solution. We are not supposed to further solve this differential equation. That is the game involved in this. Therefore, the solution of given differential equation looks like 6y square c square upon y fourth plus 3c x upon y square minus y is equal to 0, which is same as y cube is equal to 3cx plus 6c square. Now this is the trick, this is the technique. Just to deal with the differential equation, we have considered P as yet another parameter which is dependent on x and y, but we are not giving real attention to dy by dx ness of that P till this stage. In fact, we are not solving this differential equation to get relation between x and y. It is going to be wrong because already you have arrived at 1c. See, another way of looking at it is, in this case, you have 1c with you, that is the integration constant, and order of our differential equation is also 1, therefore 1c is good enough. Therefore, whatever we are doing is going to be correct. Replace P by the relation that you have, and that is what is the solution. And maybe if you differentiate, if you integrate this relation, you will get, suppose this is integrable and you integrate it, and whatever relation you will get is not going to be the solution of original. It is not going to be the solution of original because you are integrating 2 times in this stage. Once you integrate this again, we are supposed to have the final solution in terms of only 1c. Problem 2. P square y plus 2px is equal to y. The answer for this question is y square is equal to 2cx plus c square. Y square log y minus xyp minus p square is equal to 0. Answer is log y is equal to xp plus c square. Now the last in this form, fourth, x p cube is equal to m and p. काय?
सर ते तिसरं एकदा दाखवू शकता का?
जरा. X is equal to m upon p cube plus n upon p square. Okay, so 1 upon p is equal to minus 3n upon p fourth dp by dy minus 2n upon p cube dp by dy. This implies dy is equal to minus 3n upon p cube plus 2n upon p square minus sign outside times dp. Integrating you get y is equal to 3 by 2 m upon p square plus 2n upon p plus c. Now this is one relationship of p and c, and this is relationship of, this is x is equal to f of y. Y is not there, so y comma p. So this equation talks about p as a parameter, which is differential coefficient. This equation talks about p and c. So it is not possible to eliminate p from these two equations. Okay, so these two equations simultaneously, existence of them simultaneously is the solution of differential equation, parametric solution of differential equation. Because we cannot find out p is equal to from this and substitute back here, therefore this p and this p is same, therefore existence of both simultaneously is a solution, parametric solution, and you put different values of p, you will get different solutions of the given differential equation. So that is what is also acceptable, simultaneous existence of these two equations. So what are the two parameters? Eventually we have p and c, but if presently we are not able to find the value of p and put it in the equation 1, therefore we are saying simultaneous existence of these two equations is the solution of differential equation.